Good morning, and today we're talking again about the generator effect. So if you remember back to the last video, if you haven't seen the last video, you probably should go back there first. But remember that the generator effect is, well, essentially what happens in a generator, except in a generator what we're doing is we're putting in mechanical energy to spin a coil of wire in a magnetic field. And generator effect, Faraday's law, essentially, tells us that we'll induce a voltage across the coil spinning in that magnetic field. And with the generator, that's the end product, right? We want that voltage, that electrical energy, so that we can power circuits. In a DC motor, well, we still have a conductor spinning in a magnetic field, and so we still induce a voltage on that coil. And the added detail here is that the generator effect induces a voltage that will oppose the source voltage. So whatever the source voltage is, so I'm circling it here with my quote-unquote laser pointer, the source voltage polarity is opposed by the polarity of the induced voltage from the generator effect. We learned that just like with Faraday's law, just like with generators, if you're spinning things faster, so if you have higher velocity on the rotor, then you're going to induce more voltage, so more of this countering voltage that we see here. And that will tend to cancel some portion of the source voltage, and there will be a lower net voltage across the armature. And that net voltage, that V sub armature here, is the thing that's going to determine how much current is actually flowing through the armature of the motor, and that in turn is related to the amount of force, Lorentz force, that it feels, and thus that tells us how much torque it's going to develop at any particular time. So let's look at a couple of situations that are going to illustrate how the generator effect works in a basic DC motor setup. So I've copied over a few of the diagrams from previous slides so that we can have them for reference, and so I can mark things up here. But let's consider a situation where we have no mechanical load on the motor. So in other words, whatever we're usually powering with our motor, like a propeller or a fan blade or a wheel or whatever it happens to be, let's say that that's not connected. We're just letting the motor turn freely. It's only having to turn essentially itself. And so the load on the motor is very, very, very low, close to zero. And we start up the motor. So in other words, we connect our DC power supply here. You can imagine closing a switch or something that we would put in one of these arms. Let me just actually draw that in. And we'll change the... There we go. So yeah, if we had a little switch like right here, so a little SPST switch, we could close that, and that would be starting our motor, right? We're applying our DC voltage to our motor. And remember, the motor assembly is, or the motor assembly, the whole DC motor is this piece. So we've got the armature right there, and we've got the field winding here. All right, there we go. All right, so these are the four equations, 1, 2, 3, and 4, that are going to allow us to sort of reason our way to the behavior of what the DC motor does in this situation and many others. Okay, so the motor has just started. So what can we say about the velocity of the rotor in that moment? Well, if it's just started, it hasn't accelerated. So the velocity of the rotor, right, this little V right here, that's going to be relatively low, right? So remember, my handwriting is not great with this thing, so I'm just going to draw arrows to represent. So V is very low, okay? And because B is more or less constant, right? This guy right here, right? He is constant. I guess I have to kind of write that out. So constant abbreviate it, there we go. Constant, and why is that? Well, if we look over here in our DC motor, right, again, right over here, we've got a DC motor type here, which is common, where the field windings are in parallel with the armature, electrically in parallel. And so whatever we're doing on the armature doesn't really affect the voltage difference that's applied to the field windings, because the field windings are in parallel with the armature, and they're also in parallel with the source. Right, there's our DC source. So field windings and source are in parallel, so the voltage difference across the field windings is always the same, which means that the current through them is always the same. There's a couple of things to consider there. Details, though. Generally speaking, just the same. Okay, so constant magnetic field, low velocity when the motor is started. So if velocity is low, that means, according to this proportionality, that's, remember the little fish here is proportional to, that means that the counter voltage is also low. And if the counter voltage is low, that means that it cancels in this equation, in equation number 1, means that the countering voltage, if that's low in this situation, then it cancels very little of the source voltage, because the source voltage is always whatever just the battery supplies. And that means that the V armature is about as high as it's ever going to be, right? The net voltage across the armature is the difference between the source voltage and the countering voltage. And the countering voltage is always going to try to counter, right, cancel out the source. And so the biggest that the net voltage across the armature can ever be is equal to the source voltage. And here it's very nearly equal to the source voltage, because we're at a point where there's, almost zero velocity on the rotor. Okay, so if we have a V sub armature, right, our net voltage across the armature being pretty high, well, we can go back to V equals IR, right? That still works. The armature windings have some resistance, we have some voltage, and so if this is really high, like we found in question 1, or rather equation 1, then that means that the current is also high through the armature, okay? So current being high, if we come over here to equation 2, well, if current is high, and remember B is just constant, then the force and thus the torque on the rotor is also going to be high. All right, so let's just sum up. We've got low velocity, which means low counter voltage, which means high net voltage across the armature, which means high armature current, which means lots of torque on the rotor. That's a good thing for our motor, right? When we're at low speeds, we want to get up to whatever our running speed is quite quickly if we can. And so this situation where we have relatively high torque at low RPMs, low rotor velocity, is a good thing, okay? So let's consider a situation like this next. All right, so now a mechanical load is then applied to the motor. So imagine that after just sort of running freely all by itself, the DC motor, I don't know, via a clutch or engaging some gears or whatever it is connected to the thing that we want to rotate. Again, a wheel, a propeller, a fan blade, something like that. Okay. So imagine you're going along, humming along at some constant speed, and suddenly there's this big load that now needs to be rotated up to that same speed. Well, what's going to happen in the short term? Well, the rotor speed is going to have to slow down, and hopefully you get plenty of torque in response to that to get the thing back up and running. But the immediate effect is that the rotor speed is going to drop because you've attached this thing that it now needs to rotate when it was rotating more or less freely. Okay? So again, we've got our 4 equations here. I will forego labeling them, but I'll work through them the same way that I did last time. Okay, so you apply a mechanical load to the motor. Okay. Well, when you apply that mechanical load, you're going to drop. Ooh, something there. You're going to drop the velocity of the rotor again. That drops the counter voltage. Okay. What that does again is, right, if this is dropping, then this is going up, right, because this is canceling less of the source voltage. If you're going up in terms of net voltage across the armature, then you're going up in terms of its current. And if you're going up in terms of its current, remember B is constant when you have a field winding in parallel with the source and the armature. So if the current goes up, you get more force on the rotor, and that means more torque. Now, an intermediate step that we kind of didn't consider here is what happens when things are just humming along more or less at top speed. So let's consider that in the context of this slide. And excuse me while I get out my colors again here. I'll erase all of that. Bring back my pen. Maybe. Okay. So let's start over again. Let's say we've accelerated. So this is not the case anymore. We're not just starting. We've accelerated all the way up to our maximum velocity of the motor. And this is no mechanical load. So sort of between step 1 and step 2 that we just discussed. Okay, well in this case, the velocity of the rotor is very high. So let me do an up arrow here for velocity. Okay, B is still its old constant self. Well, if velocity increases, that means we're inducing more voltage, and that means we are inducing more countering voltage in our DC motor. That means, of course, over here in this equation, that's the same counter voltage here and here. Right? So whatever happens to this happens to that. So if this is big, it's canceling more and more of the source voltage. Okay? Theoretically, it could cancel all of it, though because the motor is made of stuff and there's friction in the bearings and things like that, you're never ever going to quite cancel all of it. But you're going to cancel a lot because the counter voltage is at its maximum value because we're spinning along with no load and no mechanical load at maximum velocity. So that means that the net voltage across the armature is as low as it's ever going to be. It's close to 0. And that means that if that net voltage across the armature is really small, then the current through the armature is also going to be very small. That means that this current, same current, right, is also very small. B is constant. And that means that the force, and thus torque, on the rotor is also very small, right? So the feedback effect that the generator effect creates is really helpful in sort of regulating the speed of a motor. When you have a situation where it's just started and the velocity of the rotor is low, then you get lots of torque. And that's good because you want the motor to accelerate whatever it is that it's attached to and bring it up to its running speed. In addition to that, if you ever get a situation like we did here, where you suddenly have an extra mechanical load, somebody throws a wrench into the gears, or you've engaged a clutch, or whatever the case may be, well then you get more torque because that causes a drop in the velocity, which means an increase in the current going through the armature, and that means an increase in the torque. So this is the summary slide for all of those things, okay? And hopefully you found this very informative about the generator effect and its effect on the velocity of a DC motor and its effect on the torque of the DC motor. Note that if we increase the source voltage, this is a last little tidbit, well, that's going to increase the maximum velocity of the rotor because the velocity can rise higher and create more counter voltage, which then can rise to try to cancel the source voltage. Anyway, We'll cut it off there. We're at about 15 minutes. And when we come back next time, we'll talk a little bit about a more modern variant on the DC motor, which is the brushless DC motor. Quite different in its operation, though still just takes DC energy as input. Thanks for listening.